Okay, hello everyone. Welcome to a working session for our physics project, except that the methodology and paradigm of our physics project has extended to other areas, and for the last few months, been working on implications to metamathematics and the amazing interplay between ideas in metamathematics and ideas in physics. Okay, so Nick and James here said that they have made something which I'm very keen to see. Which is we have some empirical metamathematics. We have a data from the metamath system, not metamathematics. It's simply a system called metamath that has about 42,000 proofs in formalized mathematics in it. And the goal was here to get a sense, oh wow, of what that structure looks like in the structure of the 42,000 theorems. So what we've got is a theorem dependency graph, right? And is this?
Well, the key one is the rainbow one in the middle of the notebook.
Okay, but let's just understand what these are. So first thing is, this is an adjacency matrix, but why is it lower diagonal like that?
It's a directed graph of dependency. You can't go back from the axioms to the theorems. Just go from theorems to the axioms.
But hold on a second. But these are many lemmas. I mean, so any given thing here. So once we have a theorem, it is hanging off other theorems. Oh, I see. You're saying once I get is that a feature of it being a partially ordered set? Is that necessary that well, okay, but this is showing basically that many things depend on the first few theorems here. Is that correct?
Yeah, it's a pre-logic set theory.
Right, so what's this, for example?
Maybe numbers.
Okay, all right. What's this guy here?
Well, this is just random matrices that we can produce from the graph.
I mean, look, what we did at the beginning was we just threw the kitchen sink at this, seeing how we could represent it.
Okay, but what you like best is the rainbows. Yeah. What are the rainbows?
So this is like the mist that you suggested, where we've removed the edges and we just plot the vertices. But what we did was we color coded it using the same color coding as before. So these colors correspond to these different fields of math, which shows actually some interesting behavior in that sense.
Okay, but this is not the placement of these points is not a graph embedding. It's a dimension reduction. Is that true?
Yeah.
Yeah.
Yes, this.
Okay.
But we've tried with the embedding too. It's like the black mist above. It's the embedding one.
That's one embedding. Yeah.
So is this still it might be alive. You didn't tooltip everything, did you?
I think like the rainbow one is tooltipped.
Yeah.
Well, those are also tooltipped. You just have to actually find the pixel.
They're small. Yeah.
Tiny.
Okay, so hold on, let me think about this for a second. So when there are tendrils,
yes,
those are poorly connected parts of math, basically.
Well, let's just review. Okay, especially maybe for the rainbow one, right? Proximity between nodes, in this case, Nick, what precisely does the proximity express when two nodes are very, very close to one another?
There's a graph embedding here.
Well, in graph embedding, it's probably density, I guess, because it's spin elliptical. Density of connectedness, edges, so on.
Okay.
I want to find out what's in the tail. Yeah. There was an axiom I saw in the tail.
Yeah, it's either axioms or some. Yeah,
how can there be axioms in the tail? Like the axiom of choice might be in the tail somewhere because so few things depend on it.
Yeah.
Why isn't this finding stuff?
Because the points are small.
No, I know, but it keeps on flashing things. Yeah, about people asking to zoom this. Okay, hash GE2. So these are names of theorems that we're seeing in here.
Yep.
Unfortunately, to folks asking to zoom the notebook, that's not going to help very much. In fact, I'm worried that it's going to make everything fail here because we're dealing with a very large point cloud. So I wonder whether we have any way to we could certainly make a density function from this. Is that, I can't tell, but there's something there. Is a little glitch on my screen or whether it's a blob of theorems. E03AN. Can we look up E03AN and find out what it is?
Sure.
I don't know why this is not showing tooltips better. This is one of these cases where I'm like feeling like put on the VR headset and for a few minutes and try and explore. I haven't fired that up for like a year and a half. I can only be in it for 10 minutes before I get totally motion sick.
Sure.
I'm not sure we'll be able to. I'm not even sure that we could get this data in there. Okay, so there are. Okay, let's go look at the rainbows. Okay, so this is a spring electrical embedding of all theorems in the MetaMath database.
Well, and there's syntax definitions in there too, right? And there are axioms in there.
Yeah,
okay.
Basically all the statements.
We could clearly color, and that would be useful. We can clearly color the axioms and definitions, which are entangled up in here, but we can color them differently from the other points.
We could do that too. Actually, Nick, in the rainbow, what would the axiom be? Well, no, okay. It's still colored by the area of math, probably.
Let me just I'll zoom this a bit. Let me go ahead and read this in. Is that a good idea or is that disastrous?
Yeah, it should work. It will take a while, but it should work.
How long is a while?
Less than a minute.
Okay. All right. Okay, so that's this. Okay, that's the thing we already computed. That's the out component sizes.
Yes.
Is that right?
Yes.
Okay, now what is this creature here? This is the dimension reduced point positions.
Yes.
What on earth does the dimension reduction mean? How are you getting, what is the raw material for the dimension reduction?
It's the distance matrix rows. So 2 points are close to each other if they're
Oh, wow.
distances to other vertices is similar.
So that's actually pretty good. I mean, so what it is every point has a 35,000, 42,000 dimensional vector associated with it, right?
Yep.
Yeah.
And this is dimension reducing that. Well, that's an interesting thing to do.
And then they're colored by areas of math, as before.
No.
Well,
they're covered by. No, they're covered just by this. What is it? Hold on. By this distance, right? There's the vertex list. F rows, just outsize component size. That's how it's numbered. So those red ones are axioms because they have low vertex out component size.
Okay, so what we're seeing here is that the dimension reduction system, which presumably picks up on various attributes of the 42,000 dimensional vector. In this case, what is that? Where it said, you have some very strange tool tipping going on here. What did it say? It said out 33 in a previous session. I've never seen that before. What on earth is that? I have literally never seen that before. It's an interesting feature. Am I running 13? No, I'm running version 13. Mysterious. Look, this dimension reduced thing, we should try that for the Euclid ones, because I haven't tried that. I'm not. What do we think this kind of swirl means? And what's the difference between this one and this one?
I think it's just a quirk of the algorithm. And those are just projections because I dimension reduced to the 3 dimensions. So there are 3 projections, 2D projections.
Okay, but so, what we're seeing a bunch of dust here.
Yeah.
I'm not sure what we understand from this. Let's take a look at a few other things here, and then let's come back. Okay, so this is the Pythag. Is that the Pythag? Yeah, that's Pythag. So in fact, we want probably the reverse of this graph, right?
That's right. Yeah.
Okay. So this is the proof of Pythagoras' theorem. Prime is asking, why is the dimensionality so large? Because there are 42,000 theorems in this database. And what we're seeing in each of these vectors is we're seeing zeros or ones, depending on whether the theorem depends on another theorem. This is a representation of the adjacency matrix for the graph, for the adjacency matrix of the graph, basically. So it is theorem
distance
dependence.
matrix.
Okay.
It's actually distance matrix.
Oh, okay. So fine. So each theorem, by the way, that's a little weird because I think 1 over the distance will be a better measure. Don't you think? A theorem that's nearby or some power, I don't know. I think a bunch of these kind of network things have different powers of the graph distance. Right. So because what we want is that a theorem that is right. Okay. So this here is, okay, I don't understand. What's that? Oh, okay. That's the edge. That edge is the actual, that edge is the theorem which has this dependence, right? Which explains that dependence. Is that correct? Nick, is that correct?
Yeah, somehow.
Okay.
It's a statement. And vertices are names and edges are like statements.
Okay, but what we want is to label the axioms and the definitions up here, right? So what are these? Are these axioms or definitions?
Those are inputs to the theorem. So like the Pythagorean theorem depends on some ABC, for example.
So those are variables. Those are what
Yeah.
we've been calling variables.
Yeah. Well, Metamath also calls on them variables.
Okay, but where are they in this? Okay, is this the one level graph or is this the multi-level graph?
It's one level. It's not expanded. So all of those lemmas can also be expanded potentially.
Yeah, I understand. But so this is saying how do we get the actual statement of the Pythag thing? Where is the statement of Pythag? Is that down? Is that on this edge here?
Yeah. You can try, like, instead of proof graph, syntax tree, and you'll see it's more nicely formatted at the root. Pythag. It's like on the top.
Okay, so this claims to be a syntax tree, and this here, A is an element of complex numbers, B is an element of complex numbers. So how do I extract from this tree the root of the tree? Isn't it
Just tree data
of what? Of the
of a
tree?
tree. Yeah.
Okay. Okay, so here it is. What on
This
earth
is
is all this stuff? Okay, so what does this mean? So this is an assertion O is an element of pi over 2, comma, minus pi over 2. This here is going to be a statement that says z squared equals x squared plus y squared, always a good sign for a Pythagorean theorem. But what do these things here mean? Not equal to c.
Well.
And b is not equal to c. And O is an element of that. But how do we know what the O? O is b minus c, f, a minus c. So A, oh, I see. This is wild. Look at that. The way they're doing the two-dimensional plane is with complex numbers.
Mm-hmm.
Okay. I wonder how Pyth works. Does Pyth work in a different? So it's very non-geometrical.
Python is going to be even less geometrical.
Yeah,
right?
even less. Yeah. Some Hilbert spaces.
Right.
That's very obscure. And the fact that it has old built into it there is also obscure. Okay, fine. So what this is telling us is that this is a theorem which has blanks in it, basically, which has is a pattern theorem, which asserts something. Okay, and then so what we should see here. Okay, this is the syntax breakdown of the theorem.
Yeah.
Right? But what this graph should show us is how that theorem. Oh my gosh, what is this? Is this a piece of a proof graph or what is this?
It's a complete proof graph. So there's a proof for Pythagoras Theorem, and it's just like an expression. How do you derive this statement that was the syntax breakdown above? How do you derive it from the axioms or other lemmas?
Okay, so we can label, so some of these lemmas are definitions, some of these things are definitions, are they not? And some are actual lemmas. Is that true?
Yes.
Yeah.
Yes. Some classes, variables,
right?
Axiom lemmas.
What's a class?
You just saw one that near the top.
Yeah, basically a variable too.
So this one is a variable here. I mean, sorry. How should we be labeling these things? So if we want to label, okay, so why are there so many variables? I mean,
well, look at the statement. There's like every X, Y, capital X, capital B.
but what
C,
are
A.
they all? What are they all?
I know, angles, triangle sides.
Okay.
Yeah, triangle is not that trivial of an object.
Points. It's a complex number, so it's points, right?
Yeah. Okay. All right. So these are parameters of the theorem. But this is very different from what we've done elsewhere. What we've done elsewhere is every node is a whole theorem. So in this case, this whole theorem depends how on, I mean, our other graph is the dependence of the theorem on other theorems, not down at the level, not down at this unwrapped level where we're looking at the actual syntax of the statement of the theorem. Correct?
Well, this graph isn't that unwrapped, though. It could be unwrapped much, much further. It's still quite wrapped.
Okay, but it's less wrapped. I mean, for example, in
but
Euclid,
I understand it. It's not like this is a tag. It's not like this is in the kind of graph that we use. Yes, it's slightly different.
Okay, so let's try to understand the graph we need. Okay, so we've got the graph that corresponds to the regular Pythagorean. Okay, so just so we're clear what we're talking about. Let me see, I'm just pulling it up here. Okay, here we go. So this is the dependency graph from Euclid for the Pythagorean theorem. Okay. So what we see in that dependency graph is there are the axioms at the top, and there's the theorem down here. So what I'd like to see is the same type of graph from MetaMath, which is what we derived last year for, right? That's what this we are going to get so close to 100 here. Never got to 100 in the okay, this is now empirical again. Well, actually, this is graph. I think we should just call it. Okay, so you understand what we're trying to do here. We're trying to get okay, so we're trying to get the analog of this.
Do you want these definitions removed from the graph then, for instance?
I would think so for the theorem dependency graph. Let's just try to get something which is exactly a theorem dependency graph. Then we'll worry about the definition side of things. Okay? Okay. And then what we want to do is, in the case of Euclid, we do not have a more detailed breakdown because Euclid is just words. Okay?
Yeah.
But in the case of our own stuff, we do have more detailed breakdowns, and we have things like, you know, we can do things like this from the automated theorem prover. Right? That is a full breakdown. And that's a little different than the breakdown we're getting in MetaMath. But again, we can do some level of breakdown. But the first thing to do is the pure theorem dependency graph. Make sense?
Yeah. So for what
MetaMath graph is our dependency graph.
Is the dependency graph. So all we need to do then is to say vertex out component. Is it that way round? Vertex out component graph of this comma Pythag. Okay, and then we're going to filter that by things that have definitions and axioms removed, right? Okay, so this should be a 7,000 node. Okay, 7,500. It seems to be different every single time I do this. This is 7,500 node graph, right?
Well, the database is evolving.
Not day by day.
Come on.
Not day by day. Okay. So this, now what we want to do is vertex delete. So let's make a vertex list here.
It was updated 6 hours ago. So it's possible.
Well, okay, good. It is possible. That's really quite wild. Okay. Okay, so we have this graph, and now we'll say vertex list of pith graph, and then we'll say in that select string contains queue of we can say no, string starts queue, right? Is the correct thing this or
Yep.
df dash that? Okay, those are the definitions and axioms on which this depends. So just so we're clear, the axioms, there should be 48 axioms on which this depends.
Ding,
And
ding.
there are.
Great.
Okay. All right, so let's just make sure we understand here how many definitions it depends on. Okay.
Mhm.
$231. Okay, so now what we're going to do is we're going to vertex delete all the definitions. Okay.
Okay.
So let's say vertex delete in pith graph of select that. Okay.
Mhm.
Okay, 7,300 node graph. Okay, now we want to label the elements of that graph with we're going to want to do a reverse graph, but we're going to want to label the elements of that graph with their field, right?
Right.
Okay, so now where is our table for that? We made a table yesterday.
No, you can use MetaMath import for that too.
How?
You just ask for theorem fields. I just put it there.
Okay, so which
Nice.
piece is that? So that's your. Wait a minute. That's for a given theorem. Just tell me what to type. You're saying in your MM.
No, that resource function you have on the top. Instead of asking for set mm, just ask for theorem fields.
Okay, resource function here. This one? No, which one? Up here. Okay, resource function. This specific one here.
Yes. Instead of set mm.
How is it capitalized?
Capital T, capital F.
So what is this going to be? Is this going to be an association for all of the theorems?
Yes, it should be.
Okay, but that's the
Yeah,
thing
show
we had a
us
mapping
taking
for
slow.
yesterday.
Yeah.
This is not promising. Okay, so let's just remember, so yesterday we had got, okay, the first thing we're trying to do here is we're trying to make this Pythagorean theorem dependency graph, okay? Color-coded theorem dependency graph.
Yes.
And then we want to understand what the corresponding graph is for the complete set of, theorems. Make sense? But let's do the junior case first.
Yeah. Okay.
With only 7,000, as opposed to the full case, which is, so that's the vertex count of MetaMath graph, which is about 42,000.
Mhm.
Okay. Okay. So how do we get, this was what we were calling MetaMath a sock before, right? Am I right?
Yeah, well, can you try it again? I don't know, maybe it works for me.
Okay, all right. So what should I call this?
Is that Metamathematics? No idea.
Does it work fast for you?
Oh, yeah.
Why don't you put that in the data section of the Dropbox as a WXF? And we'll separately debug why this is not working. Okay, we already tried to do this yesterday, so let's make sure that we have let's see, what have we got here? Oh, for goodness sake, we have got to use consistent things here. Look, okay, so this is definitely not working. So that's a separate thing to debug. Okay, so this is what we had before. Let's get the exact same things from before, except you say this is wrong right now, correct? So we don't want to use this.
Maybe not wrong, just old.
But should we use it or not?
Okay, look, what we're trying to do is get a version of this graph and the related graph. Okay, so let's be clear about let's just get a version of this that we freeze now, so we get a version that we can consistently use.
Right.
Well, in our data folder, we already have some graphs.
Okay, but is it the right graph? I mean,
well, if you want a frozen one, so
I want a frozen one. I do not want to update it hour by hour. Right? I want a frozen one. It doesn't matter. Formalized mathematics may be advancing, but it doesn't. The advances hour by hour are not relevant to us.
So we'll just take the one saved there.
Do we have all the other things associated with it, like the ASOC and so on? Because we need a consistent one of those. Otherwise, we can't have it misaligned. Do you see what I'm saying?
Well, ASOC have to be crawled again.
Okay, but we can't do that independent of getting the graph, because the vertex numbers have to be aligned, right? Or
No, we just remove those that have no field in that association from the graph. We can remove them.
Okay. All right. Okay. So what are you proposing we do here? So you're proposing that we get.
Well, you can use this cloud get, and that would be the same number of vertices as far as I know, in the association and in the graph.
No, I know, but that's a different number. That was what we did before, and we concluded it was wrong. Right. So let's not make this mistake again. I mean,
how it is wrong? It's just
okay. This was 35,000. Okay, let's not use this one. We've got the one with 42,000. That's the one we're going to use. Let's use that one. And if we have to, okay, this thing, you're saying this thing is okay, mysteriously slightly longer.
Yeah.
Okay, but we got the one with 42,000. We got everything consistently done for the 42,000 one. So let's use that one. Am I making sense?
Yeah. Why? Yeah. Why shouldn't we?
Okay, so where do we get the 42,000 one? Where is the 42,000 one? Do we have? Let's get our own frozen copy of the 42,000 one now, and our own frozen copy of the association now. And then let's
have one. We have one saved.
Okay.
The data folder.
Okay. Let me find it. Okay, what is it called?
ZMM graph.
.wxf.
Yes.
Okay, that's the one that for some mysterious reason was taking forever to import.
I think I've made it work somehow. But, well, maybe not. Maybe it was distance metrics. Okay, let's try it. Maybe I compressed it.
Hey, this is ridiculous. It's a 10 megabyte thing. It should come in instantly. There's something wrong here. There's something wrong that's causing both of those to fail. What is going on here? Can you try importing the same file?
Yeah, I remember trying it. Yeah, it also failed like that. It's not gonna load. I couldn't figure out why.
Okay, we need to report this. Okay. So it's not even interrupting. Something is very sick here.
Yeah, giant graphs are not like doesn't like it.
Which?
I don't know, something wrong with the graph. Giant graph in general. I don't think it's this particular one. I don't know.
Well, what should we do?
Okay, let's figure out what to do. We're going to save it as an MX file, not a WXF file, and let's get. Okay, here's what we need. We need the consistent graph and a sock for a particular version. Okay, we either have to decide we're punting and we're going to use the old one from a year ago, or we're going to get a new one that's a 42,000 sized one and use that. Which are we going to do? I think we had the 42,000. Go ahead.
I would use the new one.
Okay, so fine. So let's
do that. I don't see any
that.
reason to use the old one.
Let's be consistent and use the new one. Where is the new one?
It's the one you already have, like MetaMath graph. In the MM dependency graph, if you ask for it, that's going to be the newest.
Okay, let's be very precise what we're asking for, because let's fill out what we want. Okay, how do I get that?
So we have this MM object, right? Loaded.
No, I don't have an MM object. I have nothing. Where am I getting the MM object? You mean this thing here?
Yeah.
Okay, this thing here, right?
Yeah.
So let's try to get the okay. Okay, so this is that. That's the MM object, which we already imported.
Maybe not.
Well, we did import it before, but I think we're now doing it again to make sure that we can actually do it. But I would like to save this in an MX file. Okay, is there any reason not to do that? So we can save it consistently in an MX file and store that in the cloud. Do you understand what I'm asking?
Sure.
I mean,
yeah, you can. You can just call put it and include definitions too.
Well, or if it's eventually going to be a cloud object, we could as well use this. Yeah, I think we just did this before, and we just did. Okay, we just did exactly this, right? Which took a while. Okay, I'm going to kill this because Well, we're going to need it. Are we going to need this thing in a minute? We are, aren't we? Because we're going to need it for not only the dependency graph, but also other things, correct? But we were not able to get the theorem fields from this. Is that correct?
Yeah.
Right.
So what happened? So how are we going to get the theorem fields?
No, just Metamathematics. It's no different.
No. It is different. It's of length 35,000, whereas this is of length 42,000.
Then I have to crawl it. Because
wait,
this Metamathematics somebody crawled before me. I have no idea how.
But if we're going to use the old ASOC, why not just use the old graph?
Right. I mean,
because it's like you can't label anything that you get in the new graph, basically, field-wise, right?
Yeah, that's right.
Well,
so why are we using the new graph?
Hold on. Okay. Question. What is in the new graph that's not in the old graph? That's of,
7,000 theorems.
I know, but are they relevant? Do we have any intuition about that? Are they relevant to Pythagorean theorem?
Well, they're relevant because they added things which allowed one to prove more of these famous theorems. And what we have done with the famous theorems thing is we've used the new graph. So we really have to use the new graph for the other stuff as well.
Okay.
See what I'm saying?
Okay. But then Nick's saying he has to
okay, where did we
crawl it again for the fields?
So let's look at how that crawls. Okay, how to crawl that. Or we can go back to the old code from the Euclid post that did that crawl. We can go find that. Should we do that?
Well,
maybe it's that cloud get link. Maybe it contains the code that crawls it.
Well,
not just the association.
Yeah, let's look at it. Why is this taking so long? I mean, is this taking as long for you?
No, it's not like that. It takes less than a minute. Something is not wrong here. Something's wrong.
It worked before. It didn't take that long last time, even when you did it, Steven.
Well, can you put this, if you've got this, Nick, can you put it as a save it as an MX file in that Dropbox area?
Okay. Maybe that setMem object is already that. setMem object.mx.
Okay, well, let's try it.
Just maybe it's not included. Doesn't include the definitions. I'm not sure.
That came in instantly. 35 megabytes came in instantly. So we got a bug here.
Yes.
Which we should get somebody to look at.
So what is it? Can you show me what the MMO?
Do we just say, what is it?
Yeah.
Seems to be blank. Oh, because no, because it's an MX file. So it it's an MX file. So we need to know what was saved in it.
This is the MM object, Metamath object.
Okay, what's it called? MM object?
Just MM, yeah. I think it's not going to work because there's no definitions.
Okay, we got a big mess here. So let's start from scratch. We're going to start from scratch, and we're going to try and do this. Okay. So where is the origin of all this stuff? What do we have? What was the original thing? There was a metamath import running against the setmm file, correct? Let's take it from the top. Let's start from that. Let's do that. Okay, is that right? I mean, because what we've got here, okay, this claimed to be, I don't understand why this doesn't work here, but be that as it may, where is this getting its data from? Do you know? You know why it's working for you? It's because, yeah, I understand. But the reason it's working for you is that you have a local cache, I think.
Well, it was working for you too, right? You imported it before.
I'm going to restart this. We're going to take it from the top again. Why is this taking forever? What is happening here? Okay. Okay, this is another bug that this has been. Okay, we're going to just restart everything. I wonder how big this got. This is probably. Okay, let's take it from the top again. We really need to get to what we actually need to do. So, okay, what do you recommend? Okay, are we going to start with where should we start here? Should we start
from that metamath import function?
Okay, all right, that's in MM35. Okay, for 93 rather.
You could just follow the documentation. I can send you a link. Some examples.
Okay. All right, so let's go from the top here. Okay, so we're going to redo this. Okay, so we'll do this first. Let's see if that takes ridiculously long this time. And let's actually, we're going to put okay, and then we're going to get the dependency graph. Now, you're telling me we cannot get the ASOC thing that is a mapping. So what we'll need for the things we were doing before is we have code that takes the graph and the association, because that's what we used elsewhere, right? So what we had in the other parts of what we were doing, we were using exactly the same variable, metamath graph, right? Am I right? Yep. Okay, so we're using exactly that same variable, and because that's what we did for the famous theorem stuff, right?
Yes, yes.
Yeah, right. So because we have to use the exact same thing, otherwise we're going to get messed up again. Okay. Well, you were right. It was a minute.
You have time in it too.
That's not really. Oh, for God's sake. I thought that had lower precedence than that. What do I know? Okay. Okay, there we go. All right, there's our graph. Okay, now we can do all these things that we were doing up here with that graph. Okay, so now what we want to do is this coloring stuff here, for which we need the other things that we had done before, which was this Metamathematics sock, right?
Right.
So how are we going to get that?
Well, do we need to crawl it again?
Yes.
So
okay. Do we know how to do it, or do we not know how to do it, or do we need to look at the old code?
I don't know. I don't know. We have to look at the old code.
Okay, fine. Then that's what we have to do. Okay, hold on. Well, this is going to be a big, long dive. I mean, this is going to take at least an hour to do this if we do it this way. So if that's the only way we can do it, then that's what we have to do.
Is that the only way we can do it, Nick?
I guess. Well, right? Yeah. I only found the association of the code for it, or maybe I haven't really looked.
Okay, let me see.
So in that Euclid block archives, it's in the programs. It's not a program, it's just association dumped.
In which, in what? In one of those programs?
Yeah, programs 07.
Okay. Even that's not coming up. Why not? Oh, that's just a dump of the association.
Yeah.
Why are those things blank? Oh, because it has no sections. Okay. Okay. Well, what about the click to copy for those pieces? Didn't we have, hold on 1 second. We've got that. Okay, hold on. Didn't we already have okay, this is a total mess. I mean, we already had a bunch of code that we had done like 2 weeks ago for this with the old graph. We then decided we're going to use the new graph. Okay, let's take a look here. Okay. What we had previously was, as I showed before, right? This is the previous version. Was right here.
Yeah.
Okay. This is what we had from 2020. Okay, with those two cloud gets.
Yeah.
Unfortunately, this is not enough, because if we do this, we don't get a bunch of those famous theorem things. Okay, so what we need to do is learn where this came from. That's the piece we don't have. So we have this part, we have, right?
We have the graph.
Yeah, we have the graph.
We just need a new association.
Right.
Yeah.
Okay, so let's figure out where that came from.
Okay, how do we do that?
Well, we go back, and I told you it's going to take about an hour. Okay, let's start reconstructing this. It might be in, let's take a look.
Seems like Mano got it from me, but I don't remember.
Got the code from you?
No, the data set with the sections.
Oh, God. Great.
Oh. So there's no code. It's just a cloud get of my data set. Okay, hold on.
Well, that's good. At least we're coming to the right place here. Okay. This is stuff from 2020. I really wanted to get on to some other things that we needed to do also here. So,
okay, well, let's discuss briefly. If it's the case that we absolutely need to do this before you can continue writing the empirical section, then it's worth doing now. But if there's something that, if you want to return to this later, there's something else that we also need to do before you can keep writing.
oh, hold on. I'm just looking at what we did in 2020. Wonder why this was. Okay, well, we've advanced a bit since 2020. That's good.
Hold on, one question. Okay, we just want to make, at the moment, we just want to make the graph for the Pythagorean theorem, right? What is the difference? Let's say we make the graph, let's say we make this using the 35,000 node graph or the 42,000 node graph. Do you think that those two graphs, we don't know? So that's why you want to err on the side of caution and use the larger graph.
Yes, because we don't know.
Yes, because we don't know. Fine.
And also, yeah, I mean, we can clearly make the thing with the smaller number of nodes. And look, the sequence that we need is we need the direct dependency, theorem dependency graph. We need the full theorem dependency graph, both of which I had versions of in the Euclid post. Okay, then we need the essentially the what are we going to call it? The sort of statement level inside statements dependency graph.
What's an inside statement?
The thing that you were just showing at the beginning of this meeting. Okay, there's the thing wherever it was. This thing here. Okay, this thing here is exactly that. Okay, that's what we needed for this. But what we needed, what I was just saying is, we need to be able to see which pieces of this are. So this is the unrolled version.
No, it's not. This can be much further unrolled.
No. This is the analog, as I was saying before. This is the analog. This is something which is much closer down, closer in to actual theorem statements, whereas this is pure overall whole theorem dependency. Do you get what I'm saying?
Yeah, I consider that much more rolled up.
Okay, well,
rolled up, right?
Okay, look, whole theorem, this is the first thing. Whole theorem, direct theorem dependency. That's basically this graph here. Okay? Did you understand?
What does whole theorem mean?
It means what we were doing before. It means the same thing that we're doing with Euclid. It means that theorem 128 refers to, in theorem 128, it refers to theorem 116, 115, 114.
Yes.
Therefore, those things, whatever they were, therefore those things are joined. That's what it means. That means that in the direct stated proof of theorem X, it refers to some collection of other theorems. That is the whole theorem dependency graph. That's what we want. Okay, it's the first thing we want. And we believe that for Euclid, that's the thing that we computed. And we know that, for example, for Euclid, except we say this is wrong, we know for Euclid, this is the whole theorem dependency graph, then goes all the way down to the axioms. Here are the axioms. That's the distance it takes to get to the axioms. Am I making sense?
Yes.
Okay. And this is now the thing we wanted, which is the number of copies of each axiom that show up in the whole theorem dependency graph. That's the only thing we're doing there. Okay. The next thing we need is this thing here, which is this is the whole theorem dependency graph for the original whole theorem dependency graph. But now I'm confused here again. Now I'm confused. That first level graph for Euclid should contain merely, I'm sorry, not for Euclid, for the Pythagorean theorem, should contain the Pythagorean theorem, and all it should contain is a graph where that single node connects to a bunch of previous nodes.
Yeah.
For that represent the immediate whole theorem dependency of that theorem, right?
Yes, that's right.
Okay, so what did we have? What does it mean then when we have a non-trivial graph? Let me look at this. We really, really have to get onto some other stuff. This is not what we were supposed to be doing today. Okay, in any case, be that as it may. Okay, so here, oh, I see. Okay, so this is the first level dependency graph in Euclid for the Pythagorean theorem. This is the unrolled dependency graph. Am I making sense?
Hold on. I think there's some confusion about what you mean by unrolled here. Let's say we take one of these theorems, okay? Those theorems, if you look at their MetaMath website page, those are going to have theorems in those pages. So there are graphs within those nodes, so to speak.
No, that's not what we're talking about.
That's how I understand unrolling. Like, because when you say you want it all the way up,
multiple.
Yeah, exactly. Okay. Right.
So
exactly.
This is the case. This we can call the more detailed graph. This is below whole theorem dependency.
It just has these MetaMath accoutrements to it.
Yes.
Yes.
Okay. So what we're trying to do. I think this one's for Lee, not okay. after one step, the claim is
yes,
Pythagorean Pythag depends directly on 26 other theorems.
right,
Explains here. Okay.
right.
And it's showing those other theorems.
So that's the first level dependency. You're not unrolling any of those theorems, so to speak. Right.
That's correct.
Right.
But now this graph, I don't understand. Because this graph, I don't understand why it isn't just one node going to 26 places. Oh, I see. It's because of the way we've done the subgraph. Because some of these have further dependence on something else. Okay, that's not a big deal. It's not a particularly useful graph. But this
how did you get those subdependencies though?
It's just a subgraph. It's just a subgraph. It's just a subgraph that goes one level down. And because these things which are one level connected here, that both that node and that node are one level connected to this graph. So when you get the out component of that node, you pick up in the subgraph both this direct dependence and this indirect dependence here, because you got that direct dependence. See what I'm saying? It's just a feature of the way the subgraph is pulled out. It's actually not a terribly sensible picture.
Yeah, I agree.
Okay, so this is the subgraph. What this should look like is there should be axioms at the top. In this case, there are axioms at the bottom here. And hanging down below those axioms is the theorem we're trying to prove.
Yeah, right.
Okay, and that's exactly what we should see in the MetaMath case, looking something like this. You see what I'm saying?
Yeah, yes.
That's what we're trying to get to. Okay, so this will probably be okay. So this one here, the full theorem.
Now hold on. Just to clarify, this whole theorem, direct dependency, theorem dependency, this what you've written here. This is just the first level dependency graph for the theorems, right?
Yes, that's right. That's the thing that corresponds to this. Do you understand? That's what what we extracted last time for this. That is subgraph of MetaMath graph of vertex out component there going one step. Okay, so right now, if we take this vertex out component here, okay, that's the vertex out component graph. Well, that's absolutely mistaken. Okay, that should be the same as this graph here, but it isn't for some bizarre reason. That should be the same as subgraph.
Nick, do you think there are like miscellaneous something that would be labeled as miscellaneous?
Should be cleaned up a little bit.
Yeah.
Remove some of the vertices.
Probably some.
Which ones? So this should be the same.
Well, we need an association to know which ones to remove, right?
Well, you have the code above. You can just rerun it.
Oh, that at least gives the same result, which is what we would expect. This code here. No, it's going to give the same result if we rerun this code, unless we change.
You just don't touch the graph. Yeah, just don't touch the graph.
But this is probably not right. Well, maybe. Who knows? Okay, that's because there are things in the graph that are not in Metamaths SOC.
Right.
Yes.
Right.
And unfortunately, this is doing things positionally, so it's going to get completely messed up by not doing that.
Right. Okay.
So the only thing we can do, hold on. The only thing we can do here is in Metamaths SOC here, we can say, if it's missing, Okay, what do we do here? If this is missing, I don't know what MetaMath colors is. I mean, we can put in a hack here. If we can do a lookup here, we can say MetaMath sock lookup that. And what should we put in as the value? Let's put in, I don't know what we put in, but you pick something to put in here. Do you understand what I'm saying?
0. What is it like?
No. It's got to be
colors
something. It's got to be something that is in MetaMath colors.
And what is there? All those domains.
Okay, so let's put in guides and miscellanea. Okay, this is a total hack. Okay, so that is bizarrely more complicated than we got before. So I'm saying it's much more complicated than this case here, which is what we got previously. So let's say vertex list. What? Oh, because it's got the legend in it.
There are duplicated edges in that graph.
What the heck? A graph object is expected. It is a graph object.
Maybe it's some row. Something.
What?
Maybe it's a row of graph and a legend. So maybe you need like %16 first or 1.
Yeah, maybe. There we go. Okay, and that's to be compared with what we had previously. Oh, come on.
Maybe that graph just removed some classes. Maybe that's why it has less vertices and less theorems.
Possibly. What is that? How could that be? Maybe I managed to get the vertex list thing there. What is going on here? Well, whatever, it doesn't really matter. Let's just say first of this, because that's going to give the right thing. Okay, so that's many fewer things. So now what we've got to do is okay, so what are those things? Are those all classes?
And woofs. Classes.
Why are there woofs in there?
Yeah, why is WC?
Why are they there? Because this is supposed to be whole theorems. This is supposed to be a graph of whole theorems, not sub pieces. This is supposed to be what theorem depends on what other theorem.
Yeah, just not like selected only theorems. Proof can also contain contain classes and loops in order
Okay,
to
fine.
construct.
So then what we need to do from maybe the difference between our 35,000 and our 42,000 is that. Do you see what I'm saying?
Yeah.
Well, if that's the case, then it doesn't matter if you want a proof dependency graph. You can use the old graph.
Indeed. But it also means that the question is whether when we computed the
What, the famous theorem?
yes, I mean we can try that in well, I mean, maybe we can just do the whole computation and using the old graph. Wait a minute. Here I've got, look, this is a real mess.
Why don't we use the old graph?
Because it's not going to give the correct results. Okay?
No, not for this. For Pythagoras.
I know, but then we're going to get an inconsistent set of results. Okay, so here we did this. Oh, great. That's because you told me this graph was not the right graph. Right, so this graph, we put in a new graph here because this wasn't the right graph. And then this is filtering that to make a 42,000 node graph. Okay, look, let's not do this right now. This is crazy. This is just crazy. I mean, I've told you it's going to take an hour to unscramble.
And we shouldn't do that on the live stream. Okay,
look. I'm not going to do that, period, because okay, we either have to start this from scratch, right?
Let's not do this now.
Redo the whole thing, because we've got something which is inconsistent, because what we had previously was this here, which we got from, I think that was based on this cloud get. Okay, where did setmm basic come from?
Wait, Stephen, do you want to work on this now or not?
I want to see whether we can solve this in a small amount of time. If we cannot, then okay.
Fine.
I mean, Nick, do you think you have a way to go? Okay, what? Okay. Okay, remember what we were trying to do, right? We've got very specific things we're trying to do. And okay, look, the question was, well, Nick, what do you think we should do? Since you were the one who originally scraped this data.
Well, it's not scraping anything. Well,
what's that?
I think the only thing you need to do is just remove those classes and moves. If you want like the graph that you want.
No, I know, but then we've got an inconsistent Metamath sock relative to Metamath graph.
I'm trying to find it. I just can't find how I.
Okay.
How I extracted this data. I have no idea.
And that's why I think we should not do this now. Nick should take some time to find that, at another time.
Okay. That means that we've just gone backwards in terms of what is figured out and what's not figured out. So in terms of getting closer to having everything we need to be able to make general conclusions, we have gone backwards, which is unfortunate. Okay, let's change topics then. What you had been doing previously is we've been trying to get an overall conclusion about the structure of this whole graph,
yes,
right? And that's what these pictures were,
right.
Which so far I'm not finding very useful.
Fine.
Okay, but the question is, what can we do that gets us a sense of the whole graph? beyond what we're doing without components and so on.
Okay.
So for example, the thing that we had asked yesterday is about uniformity of this graph. And I had computed some of that previously, getting geodesic balls in this graph and seeing how consistent they are. Do you understand what I'm saying?
Yes, I remember.
Now, okay, well, I think maybe, think about this for a minute. So what you've managed to do here, we've got this graph. We know it's adjacency matrix. Like, for example, I really would like to know how much uniformity or not there is in this graph.
Likewise.
Now, does this indicate that? This is giving us some measure of that. If the graph was completely uniform, this would be uniformly filled.
It'd be solid. Yeah, right. It's definitely not a uniform graph.
Right, but the ordering here is fairly arbitrary. I mean, for example, if we colored this, as I did in the Euclid post, by field of mathematics, that would help a bit. And what is the color here is showing us the distance matrix getting to, so the thing we could do here is, the first thing we could do, there's a direct dependency version of this. Okay, so in Euclid, okay, this was the very beginning of, okay, that's the direct dependency. That shows for each theorem, it shows directly what that theorem depends on. Am I making sense?
Yes.
So we could do the same exact graph in this case. Right? That's the direct dependency. Now, I'm not sure if I even give the graph, which is because in a sense, the more distant dependencies, well, let's see, I may give that graph later on. That's the adjacency matrix version of this graph here.
Okay.
And this thing here is the sizes of geodesic balls within the graph. Yeah, I don't think I give this one. Okay.
Well, we can't color this one at the moment because we don't have the new ASOC for the 42,000.
No, we cannot, but we could make this plot here if we wanted to. That's simply, that's even more straightforward than this. This is the metamath graph. This is simply for each node in the graph, that is the out component. It's a sparse array with those out component elements.
Sure. Nick, we can do that, right?
I think we can.
For something of this size. By the way, I just want to clarify this term whole theorem. You basically just mean we don't include these definitions or other parameters in the graph,
yeah,
right?
But we also don't include the detail of how, all we're saying is, like Euclid did, the proof of this theorem depends on on such and such a theorem. We don't say how it depends. See what I'm saying?
Yes. 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 Right.
Okay, so here, what we want to do is for every, it's like the out component. I don't think you can just say vertex out component to get the thing for the whole graph, can you? No. Okay, so for every element here, well, we can also use the adjacency matrix. How do we get this? We want the direct dependence. Oh, I see. Wait a minute. Why does this adjacency matrix? This adjacency matrix is just a 0-1 matrix, isn't it?
Yes.
Okay. So in fact, I don't understand what this matrix plot is. Is this matrix plot of a 0-1 values, and these areas here are just the areas that have higher density?
Yes, yes. Correct.
Okay. So this is in fact the analog of that previous plot that shows the dependence of one theorem on others. So this is saying that there are theorems here where many things depend on it. Those are popular theorems. Popular theorems to make use of.
Yeah, right. They're fruitful. Yeah.
Which again, I had analyzed that in the Euclid case as kind of the super theorems, so to speak. I mean, what I talked about those is what are the most powerful theorems.
Is the point though that if there was uniformity, that all the theorems would be super theorems, so to speak?
Yeah, probably.
Or none of them would be super theorems. But basically, this term super implies non-uniformity to some
yes,
degree.
but as we can see here, right, that's the non-uniformity of theorem usage in Euclid.
Yeah, there you go. Right.
Okay, so here. Okay. Okay. What does adding as a superaxiom do for the proofs of other theorems? Plot of the average amount of shortening achieved by adding each of the individual theorems as a superaxiom. I see. Well, one could do the same thing, removing a theorem and using only its proofs. Okay. Okay. All right. Well, I think we should look at something completely different here, because I think this is not.
No, wait. So the question is, look, it's a large graph. We can only perform so many computations on the graph. What else do you want to know about the graph that you think that we can compute? Like, what conclusions are you hoping to draw?
I think that the answer is there's a certain amount of non-uniformity in the graph.
Yes. And, based on our overall framework, there's plenty to say about that. I mean, there's much to say even given this graph.
Yeah, I know, but
so, okay, but if that's not sufficient, then what else do you want to see, right? What else do you want to comment on?
Let me think for a second. This I'm not sure. Perhaps we should work on the completely different thing that was what I intended we should work on, whenever it was, an hour and a half ago.
What?
Which has to do with this thing about implications and I think I'd started doing something on this. Hold on.
You mean about reference frames informed by definitions and
no, I mean
axioms?
I mean about the way that hold on. No, not this. This has to do with the way that implications by the way, I need to just move something back from the outtakes file into the main text because I think we're going backwards on something here. I don't want to use that colored graph that we made yesterday. Hold on. Okay.
But wait. Before we go to implies and NaN, it's like we discussed before. You were saying, I want to say something about this overall graph. Let's find some way of representing this overall graph. This is something that I haven't commented on. I still want to comment on it.
Yes,
so we have this. Please, like, what else do you want to see so that you can actually write this section?
Well, I don't know. I mean, I think, what is this now? I'm not sure how meaningful these pictures are.
I'm not either. We were just trying to actually, compute something that we can actually obtain. I mean, many results failed because it's a big graph.
Okay. All right. So the things that I was doing before had to do with looking at the local. See, this gives some indication that it is locally non-homogeneous. And, well, for example, knowing what, I mean, okay, color coding this graph will be very helpful.
Right. I mean, in some cases, it actually looks like locally it might be homogeneous, but globally it's definitely heterogeneous. It's not uniform globally.
I know.
Locally, there are some.
So, for example,
pockets.
Making a histogram of the local dimension of this graph would be interesting. That's what I started to try to do.
Right. Okay.
Okay. And I had code to do that. Do we remember where it was?
Was this from last week's live stream?
I don't remember. Might have been a week before or something. I don't know. I wonder whether we've actually got the things up, because there's a very good way to look at them as thumbnails. You just see whether they're up on the website correctly as thumbnails. Live streams of, no, let's see, working model material archives. 2022. It's a good start. Oh, I'm impressed. There's stuff here. That's probably stuff from practically yesterday. Oh, that's earlier. No, that's now. Well, we can recompute it. We're computing this thing here. That's not useful. And this is a graph and a vertex and a radius. This is what I had computed before. Okay, so this is graph. That's not what we want. Around vertex V. Around every vertex. Okay. So this is MetaMath graph. Okay, so for example, if we say Pyth ag, what's it doing? That should be computing around that node. Now, oh no. Look, I had already done this, and it wasn't all that informative. I mean, that was those plots that we had that showed the thing saturating.
Yes.
Let me find those again.
We were just looking at those yesterday.
Okay, 73 was not it. But let me just go back to 69. Okay. I'm going to go all the way back to 67. Nope, 67A. Nope. 69 we looked at, 671. Nope. 73. I'm not sure we might be able to search, but I really doubt it. 73, nope. 77. I don't think so. That looks like it's about the definitions. 78. That's that same graph again. Nope. This is not looking good. 79. Lovely, but that's not what we were looking for. 82.
It's 84. Euclid.
That wasn't one I was going to look at. Let's see. Ah, that's the Euclid graphs. Okay. So that was the corresponding. Okay. Okay. So there it is, but that's for Euclid.
Right.
So that's really a tiny version
Right.
of this.
Yes.
Well found, Nick. Thank you.
Can this be done for the whole graph?
No, but it certainly should be doable for one theorem.
Okay.
I mean, I think let's look at, okay, let's do the following. Let's say, okay, that was doable. Okay. I don't know quite what that, why that is means, why that does that. That should be, yeah, let's see what happens if we say volume. Oh, come on. Why does it do that? Okay, possible values, volume method, or identity. Okay. Why isn't it returning? That's really odd. Because this is the dimension. I just want to find the volumes of the geodesic balls going out from that point. Well, I can clearly do that by just saying,
Wait, but that MetaMath sock is outdated. We can't use that.
I didn't mean a sock, I meant graph.
Okay. That's fine.
Oh, that's crazy weird. See that? That means that after just 3 steps, we reach the whole component we were going to reach. Is that really what we expect? There are much longer proof paths. I am confused. Okay, let's see. Let's try the axiom of choice here. Okay, so wait a minute. Is this the incoming? Do we have this the wrong way around? Do we have, okay, is it in fact the out component? Yeah, the out component is those things on which this depends. That's on which the theorem depends.
Right.
What the heck is this?
Well, nothing depends on Pythagoras Theorem. Almost.
That's rather surprising, but possible, I suppose. Okay. All right, where are we at here? I mean, I don't think we're going to be able to conclude much from this. I think the best case is we're going to be able to show this picture, and that's about it. Hopefully that picture with appropriate coloring and so on.
Okay, but to color it, we need the new SOC.
Yeah, that's correct.
Yeah. So hold on. You think that with that picture, you can at least write something?
I'm not happy.
No, I'm not happy with it either.
I'm not happy at all. I mean, I'm this is kind of like blah.
Working with.
Oh, wait a minute. MM87, I say, has dimension calculations in it. Okay, this was the thing I was looking for.
Right.
This has the dimension calculations.
Yep.
So this is the undirected version of this graph. That was what I was looking for here. What's really weird is how quickly they saturate. Well, suggesting that this thing is kind of exponential dimensional. Yeah, I mean, so all of these here. I see, that's not the undirected graph. So some of those have so in the undirected graph, the thing saturates quickly. Let me think about that for a second. So the light cone of any given, the entailment cone. Okay, so the question really is, what is the dimension of the entailment cone for given theorems or axioms? So an example would be to figure out the entailment, the growth rate. Okay, so one question is the growth rate of this is the obvious thing to do, of the entailment cone for each axiom. Okay, that's the obvious thing to do. Okay, so that is otherwise known as the vertex out component. That's simply the length of the vertex out component for each of the axioms.
Okay, that sounds feasible.
Yeah, it's very feasible.
Yeah.
Okay, so let's do that.
Yes, let's do that.
Okay, where is the list of axioms? We've got the list of axioms because, for example, we have the list of axioms in here. Okay, so for each of those, we have let's just try here. Let's just say take axiom is comma 5. Oh, really? Vertex out component from those axioms, or does this want to be the in component because we've switched it around? Oh, for goodness sake. Okay, great. That's nice. This is good.
This is good.
So each one of these is showing us from each axiom how many theorems are reached in the entailment cone of that axiom.
Yeah, and there's some plateauing, but what's nice to see is for some of these axioms, the plateauing requires a few steps.
Yeah. Now, is there a more efficient way to compute this than the vertex in component of maybe what I want to say, well, okay, let's just do this. It won't take that long. Okay, let's run this. And then what we're going to do is for each of these, we will look at the growth rate here, which we can probably get. Okay, that was nice. Okay, so now let's just say, actually, we might just be able to say list line plot of association of that.
Okay. Yeah.
Percent 44. And let's go ahead and
at all. Yeah.
Well, there's some that don't make it to. Okay, so let's try here. Scaling functions arrow log. That wasn't very useful. Let's see. That is distinctly unuseful. I mean,
wait.
Okay.
I think we should. Are these all for 10 steps?
Yeah.
We should do it for more steps.
I know, but it will take longer, but we can. Let's do it for 20. And then, so some of these axioms quickly entail
they saturate. Yeah, right.
All theorems. They quickly affect all theorems. Others take a lot longer to affect all theorems.
Well, it's that they quickly, their entailment cone matures quickly. It has all the theorems that it's going to contain quickly. Okay, great. We computed it. Cool. All right, let's see if most of the plateaus are captured now. Yes, they are for the most part. In fact, you could probably have just gone to 15 or 17.
Okay, so what this is showing is that there are axioms. I wish we could tell which was which. Let's just do this. Okay, what we want to do then is
oh, I see.
okay, so basically what's happening is not much depends on the axiom of choice. That's down here.
Right.
So pretty much everything depends on modus ponens and so on.
Right.
there are things that don't depend on these various set theory axioms, and there are plenty of things that don't depend on the number theory axioms.
Sure. This is useful. This is interesting. Okay.
So for each axiom, there's a question of what the total dependence is. And then for each axiom, there's a question of how long does it take. I'm a little confused by what this is showing because, for example, if the light cone, if this was three-dimensional space, if this was two-dimensional space, for example, I think that these initial growth curves here are, well, we should look for some of these, but I'm guessing that they are exponential and then they level off. And we can check whether they're exponential by doing this thing here. That's not very convincing. I mean, the question is, are those straight lines? And hard to tell. Let's just see if they're power laws.
Okay.
I would say no. I would say they're much closer to exponential. Those would be straight lines if those were power laws, and they're not.
Right. They're not.
So I'm going to guess it's exponential and then plateaus, and we can kind of get some evidence of that by, instead of doing this, we can say here, ratios. Get the log. Oh, that's weird. That is weird.
Yeah, plot range, right?
That's weird.
Oh.
Okay, so what we instead want to do, yeah, Richard is commenting that these are like logistic curves, and I agree, but that's because they have to saturate. The question is what their initial growth rate is. Okay, so let's take a look here. Let me think for a second here. So if this graph was like a tree, then what would happen is at each successive step, there would be a constant factor more things that it reached. And so what should happen is, I think this is kind of annoying here. Let's just take a look. Okay. So bizarrely, they don't actually go to a constant here. They're continuing to increase, but at a very slow rate. Well, it doesn't look incredibly exponential because these are very few of these. You know, it looks like it has a huge jump at the beginning. I mean, the problem is that what we're looking at is something that was, you know, people just chose which things should depend on. Maybe sometimes they just said it directly depends on this and they don't worry about the indirect dependency.
It could be. That's what's difficult about this.
Yeah.
Yeah.
I mean, okay, look, maybe we should, I mean, we could wrap up here, or we could try to do the thing I was originally trying to do. Maybe let's just try.
If you want to discuss implies and NAND.
Yeah, that's what I was originally hoping to do. So let's get Oops, I misspelled Metamathematics for the name of this. I'm going to rename it just because I don't want to leave a misspelling like that in there. Okay, let's do the following then. So okay. What this is about is whether, given a statement that can be represented in terms of implies, I thought I'd actually started looking at this. Hold on one second here. Didn't I make a function that does this? Hold on one second. I thought I had made a function that does this. Hold on one second. I guess it was not here. Okay, who knows? All right, so what we're trying to do is we're trying to figure out, let's see, in this case, we've got, this is trying to say, how do we represent various expressions in terms of NAND and implies and so on? And so what I want to do is to show that if you have implies expressions, you can make direct deductions for some. In other words, if I have an expression in terms of implies, this bug, by the way, I finally tracked down this bug. This bug is going to be fixed. We will not see that anymore.
Cool. Wait, keep going. I'm trying to, I think I know what you're referring to with implies, but.
Right, so what I'm trying to do is I'm trying to say that there's a theorem that can be directly deduced in terms of implies.
Right.
But now we convert the implies to NAND.
Right.
And then it no longer.
Yeah, but this is what I was saying. This was brought up. We were discussing, definitions.
Yes.
Reference
do you know where we
going from the axioms?
Do we know where we had this? Do we know what file this was in? Was it in the definitions file?
Hold on.
Ah, here we go. Yes, it was actually.
Yes. Anyway, this was from that discussion. Yes, I remember this well. Right.
Okay. So it's in find. There's this function find logic formula, which we should put in WFR. And
right.
Okay, good. Well, this is the beginning of this thing. Okay. We don't even need to finish this computation, but this fine logic formula right. Okay, I know what to do here, I think. I don't know why this is frozen again. What's happening here? That's just weird. This should, I mean, this is doing a search for those Boolean functions. I don't know why this, how weird. That does, again, doesn't take that long. Just a minute. Okay, all right, so this is showing how these expressions, not P and Q, can be represented in terms of implies and so on.
I remember. Okay? I remember. Yes.
Okay, so now the idea is that we take an expression in terms of implies, and we can either make deductions directly. Okay, so we take an expression using, e.g., something non-universal, using something non-universal, non-functionally complete. E.g. implies on its own, or and on its own. Okay, so now we can potentially have a we can have something where, okay, so two paths. One, convert to nands and compute with that. Two, use only implies. Now, it's not obvious. Right, so if you simplify it in terms of nands, it's not obvious. Okay, so, okay, actually, simplify expression using nands, not obvious you can go backwards. To implies. Okay, let's see how that works in practice. Okay, so what we have is something like this. This is the representation of implies. Okay, so now, where did I get this from? This is, oh, I see. This is find logic formula in terms of nands for this thing in terms of implies. Okay, and now there's a question of, can we go backwards from that to get something in terms of implies? Oh, for goodness sake. Okay, so then this is, oh, I see. No, it doesn't simplify any further. Okay, so sometimes if this actually said implies, it would presumably 59. Okay, but that still contains nands.
Right, right.
Okay, so now if what we want to do is we say groupings of PQR implies arrow 2. I'd say. Okay, so then this one here would be find logic formula, this comma NAND arrow 2. Oh. Okay, so now we want to say, can we go backwards? That / dot.
Right, right.
This thing goes to implies. And we didn't get very far. So sometimes, so what's happening in these cases is actually there could be another representation of implies. Okay, so with this one representation of implies, we don't manage to go backwards. Okay, let's do this. Let's say okay, those are the simplest representations of those things in terms of implies. So let's say we were to do PQR, PQ. Okay, now, in terms of implies, so for example, that first one started life as this, purely in terms of implies, simplifies to this. Make sense? Now, the alternative would be, since 69, we could say find logic formula PQR in terms of NAND. Oh, come on. I should have done this in parallel. Let me do this in parallel.
Okay.
Oh, there's just one holdout. So most of them are going to be quite simple in terms of NAND. So let's just review what we're doing here. We've got an expression represented in terms of implies. And the question is, can we just compute in terms of implies? Okay, what the hell's that? That's one that failed. Wow, does find logic formula have a timeout? Oh, steps to 7. Wow, so we didn't manage to find that one. Okay, but let's take this and let's use this now. Okay, so a bunch of these can be represented in terms of implies, but many cannot. At least not using that way of doing it, even though we know that that first thing is in fact representable in terms of implies.
Right.
Okay. Okay, so the way we think about this is, imagine we define a higher level math concept in terms of something lower level. Can we, if we compute at the lower level, can we describe what happened purely in terms of the higher level?
Well, it's can you obtain the same statements that you obtain using that higher definition, right?
Yeah, but I mean,
and then if you can't, the question is, what does that say about the definition that you've introduced?
it just says, it's a shredding statement. It just says that you can't expect to only work basically saying, if you want to do this math, you have to go down to a lower level in this simple case. So let's take this example here.
Is that what it suggests? Wait. Suppose you have a definition and it's a perfectly nice definition. People use it all the time. People use it to come up with nice results in math. But then you compile it down some subcomponents and you try and yield the same expressions, emergently, so to speak, in entailment cone, so to speak, from the lower level, and you can't find them. Well, this is the whole question of the molecular dynamics versus the fluid dynamics.
Yeah.
Right? Okay, but the question is, if you can't reproduce it from the molecular level, but it seems to perform quite nicely at the fluid dynamic level, what do you make of that definition? That seems to have been quite serviceable, at the fluid dynamic level, but you can't seem to emulate it, so to speak, from the entailment cone from the molecular level, right?
No, it means that what happens is the stuff that's, the question is, can you describe the fluid in terms of vortices or something,
right?
Or do you end up having to describe it in terms of something lower level? Is it sufficient to just use, for example, implies to describe it? Or, I mean, let me think about this for a minute. I thought I had figured this out, actually. Let's see. I mean, we had some notes over here. Most of the code works except in a corner case, right? To have a perfect definition, you need to have some kind of conservation law. Yeah, the real question is, does the definition you have capture all relevant mathematical structures / processes?
But what's the test of that capture?
Well, that, for example, you can, okay, so let's take this as an example. This thing here is a good example of this. Okay, so this thing here can be simplified to P implies Q. Okay, by converting it by either directly or by converting it to NAND, which then gives okay, I see. The conversion to NAND is this thing here, slash dot, implies x blank, y blank, oh dear, that's what I want to do. Okay, that's the conversion to NAND. That's compiling it into NAND. Okay, now simplify it in NANDs. Okay, and the result of that is that this thing here, if we say find logic formula, that thing, comma, PQR,
okay,
gives that.
Mm-hmm.
Okay, which can be converted to this thing. So if we take this, using, where is it? There we go. Okay, so we can go back from the NAND form back to this form.
We can.
Okay, that's case one.
Okay.
Okay. Case one. Okay, case two.
Is there some way where you can just put this in one function to test it?
Yeah, sure, we can do that. But I mean, this is basically what we have. And okay, hold on. We'll get it for a bunch of different forms. Okay, so here, case two, is this thing here. And that can be simplified to this purely in terms of that. But converting to NANDs, okay, what we get is this thing here. It's ridiculously long. Okay, now okay, that simplifies to that. But now we take this and it doesn't simplify to this.
Right.
Using this form for the simplification. But I think if we were to say find logic formula, well, okay, let's try this. Find logic formula of that PQR. Oops. I think this is going to, is this going to work or is this going to fail? that's trying to, I don't know why this isn't working actually, because I would have thought this would eventually find this case here. Huh, maybe we got, let me just check that I put the right thing in here. Oh, it did find that. Okay, so if we search for it there, but the problem is we couldn't find it using this definition. See what I'm saying?
Yeah, yeah.
Okay, so one approach, so it's like a commutative diagram. So one approach is use a definition to compile down
right
to something lower level. The compiled structure could be recognizable, quotes floating around at the lower level, or it could be shredded there, and you don't manage to get the results except by okay, so I mean, I think this is the basic story.
The question is, usually we use this term shredding to describe
well, no, this
observation.
is perfectly observer. This is an observer related thing. The observer,
yeah, okay.
If the observer is merely looking for templates at the lower level, they won't find them. In this case. Even though the thing is equivalent, they won't find those templates. So let's be more specific here. So let's say this is a definition of implies in terms of NAND. Okay, we could also define and in terms of NAND and so on. Let's just take a look up here what we've got. Maybe we should do XOR. Maybe we should do the same thing for XOR. Let's find out what XOR is. I'm not sure whether XOR is more or less obscure than implies. I just worry that implies has other things going on with it.
I would presume that XOR is more obscure than implies, but let's see it anyway.
Okay, so that's the formula for XOR. Okay, so now let's do this loop. So we're going to write a function that does this loop. Okay, so we're going to start with, let's say, logic loop, for whatever that means, of an expression, vars, and let's say the outer thing here. Okay, so the first step, just give the expression, and now we want to say find logic formula, expression, vars, outer. That's the simplification in terms of the outer function. Now we want to say okay, let's see. Okay, let's do this with I'm going to assume that this thing is just a single symbol. Actually, let's just say F. Okay, so here, this is F of PQ and 2. That's that formula. Okay, so this is F goes to 2. Okay, so now what we want to do is we want to take okay, so now we want to take this that result, and we want to say that result is that thing. No, we don't want that result. We want expert now. Yeah, we want this form. Oh gosh, this is kind of a mess because we have to change that form thing into a pattern. Hold on. So we're saying we want to take the original logic expression. We want to slash dot essentially something goes to form. And then that's the thing as nans. Now I want to take the thing as nans and we want to find logic formula of the thing as nans, comma, vars. Okay, nand that. And now we want to go and take the result from that, which we might call res. We want to say that res slash dot. Actually, this is slash dot. Form arrow xxx. Okay. All right. Now, these things here are things like this. We want to convert that to a rule. So what we want to do is we want to say this slash dot. This is kind of obscure, and I don't know if it's going to work. How do we take that and make that into a rule that says p blank of each of those things? If I say p goes to p blank here, okay. Well, p blank is just pattern of p comma blank. Okay, to pattern rule of okay, so now what I want to do is I want to say expr slash dot then I want to take level expr comma -1 union that thread hash goes to pattern hash comma blank. Okay, to patternoid. I don't know what a patternoid is, but this isn't really a pattern in the normal sense. Oh, for goodness sake, thread. Oh, big mistake there. Yippee doodle do. Okay. And then this. Let's see. Okay, wait a minute. If this says LHS, RHS, then this is, okay, this is the LR case. I wonder if this is going to work. So we want to find, okay, that's the logic formula for XOR. So the thing would be to say 2 patanoid LR XOR PQ, this thing here, comma PQ. Lovely. So now if I do it the other way around,
Okay.
oops. Lovely.
Good.
Okay, so then now we need to say here form equals 2 patanoid. Well, actually, no, we don't even need to do that. We need to say here, this goes to form. So this is 2 patanoid LR. This is converting from the original expression so this is F of PQ to form with vars. And then this to form with vars. And then this okay, let's try it again. So let's try logic loop of XOR, map, PQ, R, comma, vars, PQR, comma, XOR. That's not a good sign. Let's do the following. Let's put in some echoes here. Oops, that's definitely wrong. So that got as far as this thing here. So now this, we might as well just do this here. So let's just put in res equals that thing there, and then we don't have to recompute it here. Okay, so the question is, can that be simplified in terms of an AND? Or is this the thing that isn't working? Clearly, if it needed to be that complicated, we'd never be able to find it. I don't think it needs to, I don't think anything that, I think the largest NAND expression involving 3 variables. Oh, wow. Well, let's try. I mean, XOR is the hardest function to do this with. All right, let's try this again. What's going wrong here? Find logic formula. A perfectly long thing there. PQR NAND is 2. Why is this taking forever? Oh, here, let's just do this. Dandy. So let's try the ones that we had up here. Okay, so that was successful. Right, so the problem is that we can't simplify these things here in terms of NAND, which is interesting in its own right. So I wonder if what happens, well, let's echo what form is. Oh boy. Hey, hold on. This is surprisingly complicated. I mean, this is surprisingly. Okay, let's do logic loop with just XOR PQ. Okay. So there's XOR P and Q. That's it converted to NANDs. Okay, so that goes back again. That converts back. Okay, so now let's try something like AND of this and of Q and R. Why is this taking forever? Okay, the way it's working is it's trying to find a logic formula in terms of NAND. I mean, this is doing arbitrary multi-level logic minimization, so it might be hard. Oh, there we go. Okay, so that was simplified in its simplest terms, but once it's turned into NAND, it doesn't go back again. Now, I think this logic loop thing, okay, so that implies worked fine with the logic loop. I wonder if we do a let's do this. Let's see what happens here. Okay, let's say logic loop hash comma PQR comma implies oh, for goodness sake. I don't want to have all those echoes, and let's remove the echoes. I think we know what's going to happen. What happened here? Okay. Oh. Why is there any echoing here? Just see what should I put in here. Oh, there's an echo there.
Okay.
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 That's obscure. Hold on 1 second. Okay, that's the original expression. That's the simplified expression. That's the expression as NANDs. That's the simplified NAND expression. Wait a minute. That last thing.
Yeah.
Oh, I see. No longer. Okay, so let's do the next case. PRQ there. Okay, so I claim some of these are going to return to their original form on the right-hand side. Some of them it will not be able to reconstruct from the NAND level. Okay. Okay. So what we're seeing here is some were successfully reconstructed at the NAND level.
Yep.
So this is, we take this, we compile it into NANDs.
Yep.
We then simplify it at the level of NANDs. We then try and do the reconstruction.
Get back P implies Q. Yeah.
Right. Sometimes we do, sometimes we don't.
Mm-hmm.
And one time there, we obviously didn't succeed in nailing it. So let's just go at least 9 or something here. And now maybe what we can do is, let's do this with and, for example, instead. Let's do it with and. So this is going to be a bunch of and expressions here. And this will be their, oh, I see. This is probably the one that didn't make it. We don't know whether it's going to come back in terms of, we couldn't even simplify it as a NAND expression, let alone bringing it back to implies form. Oh my gosh. Well, see what happens here. That's a surprisingly large number that don't work. Because we know that it is expressible as an AND expression. We don't have to worry that there's no way to express it as an AND expression because the input was an AND expression. Oh, this is the problem. Silly me. Look, big problem there. That should have been AND. Because that way we know worst case is, see, it's not obvious you can replace, you can get this as a short NAND expression, but you certainly can get it in principle. That this is the simplification of it as an implies expression. That's really odd. See what happens here. That's really odd. I don't understand that. I mean, unless it requires more than 9. Oh, wait a minute. Did I put this in the wrong place? I put that in the wrong place. Help. Okay, that 9 is in the wrong place. That's now. Oh, come on. Okay, why is this not being able to do it? Let's look at what this is doing. So this is, oh, here we go. That's pretty exotic. Wow. Okay, so it didn't manage to do any of those. So let's just try this, see whether that works. Now, this is translating the AND expressions. Wait a minute. Wait a minute. Why were all of these coming up without parentheses? Oh, something's very wrong with this. Okay, so let's do this. Oh no.
Mm.
Oh.
What?
And is associative. That's what's happening. And it's automatically, those expressions are automatically being converted because of the associativity band. Okay, so I wonder what happens if we make this. Yeah, so it's going to work okay with implies because implies isn't associative. Let's see. So in this logic formula thing, what we need to do is replace, and so we can have a special version. I mean, XOR will also have this problem of being associative. Okay, so what we need is an F and a, we need a F, FF, and F. This is a real hack. What a real hack. Okay. Okay, so what we want to do here is this, and then what we want to do is we want to say F. That's all right. Now here, oh gosh, this is a complicated mess. Because find logic formula has to have in it all the way back up here. Oh, I see. I see. Okay, I think I see how to do this. Find logic formula. Okay, those are the raw versions. Oh God, no. Oh, what a mess. Just a second here. So we need to do boy. Okay, hold on. This is finding no, this is not going to work. Oh dear. Well, I mean, this is going to work in the special case of implies. It's a hack.
Just to zoom out momentarily, what's the goal here, and how does this fit in?
All right, wait. How does this fit in? The whole point is, this is talking about definitions and when you can make definitions, when definitions work.
That's right.
Okay, so the point here
No,
is
that's not the point. I understand that. Bigger point. Where are you going to insert this in the MetaMath post?
In the empirical mathematics section.
Okay, this example with implies, is that sufficient?
Yeah, except that implies is obscure and it makes me worry that people will be confused with entailments. Now we can probably do a by hand example for XOR or for AND or for OR. But I think these things are going to be much clearer because the problem with this is that it suggests that, there's modus ponens is involved and things like this.
Okay, I mean, you could always distinguish implication from entailment. You could do it.
I know that, but I know, but it's a mess. And the better example is one that involves XOR. I mean, okay. Plus, I'm not that keen on the fact that all of these involve just P implies Q. Now, quite possibly, if I take one more level, I might get to something more non-trivial. I'll do one more level.
Okay.
Yeah, that's kind of fine. I mean, I wish I could do it in terms of AND and OR, but this is okay. So some of them correctly managed to get sort of fished down to, I wish I had one that was a slightly more complicated expression.
Yeah. Right.
Well, let's try one more run.
Yeah. Okay.
And then let's do I want to know the number of things in there. Let's see if I say level blah -1, heads goes to true. Yes. Select level blah -1, heads goes to true. And I say count of that, comma implies greater than 1, ampersand. And now I say P in here. Oh, come on. Come on. And I've given it only a finite length, so it has to eventually work. Come on. Oh, I made a mistake here. I made a mistake here anyway. I should have said last of hash. And here, why don't I just do time constrained? Well, this has to, you know, a minute is a very, very long time.
It is. When you're just watching the water boil.
Yeah, well, let's see. These will probably time out, but I shouldn't have given it a whole minute. I don't know if Nick is still with us, but if he is, I wonder whether he's managed to.
Nick, if you've done anything interesting in parallel while we've been agonizing over implies, and man.
Unless it's.
Oh dear.
I wonder which ones are timing out. Hopefully it will not cause the whole table to fail.
Oh.
Okay, just a minute. Grid. Oh, that's frustrating. Okay, well, let's just do this. That's really odd. Okay, well, so there aren't any double implies things there. All right. Well, look, I think we probably have achieved whatever we can achieve right here. I think I've maybe got some raw material here, but I probably need to think about it a little bit more.
Yeah.
And this was a little bit of a not a best, but
painful. Yes.
Okay. So, Will.
But we're making progress. We are inching forward.
Yes.
Millimetering forward. Yes.
All right. Well, I think we should wrap up here. So thanks, and thanks to folks on the live stream, and see you all another time.